In this video, we'll cover set operations and Venn diagrams. The first point I want to make is that every set A exists within some universe U. So if we think of our sets as circles, it exists in some universe, and we'll usually draw this universe with a box to signal that, hey, maybe this universe is, for instance, the set of integers, or maybe the set of real numbers, or maybe just the set of positive integers, something like that, and then A lives inside that universe. So the first thing we can do is we can write the complement of A, and that is written as A with a bar on top. You might also see it written as A with a little c, or A prime, and these are all complements. Essentially, if we have a set A, and this is our circle, and a universe U, the complement of A is everything outside of the set A that is in the universe. So in order to define a complement, you need a universe to talk about. So for instance, imagine if I had A, which is just the set containing 1 and 2, but the universe was all the numbers up to 5. So the universe is set 1, 2, 3, 4, and 5. Then a bar, or a complement, would be everything in the universe that is not in A. So a complement would be 3, 4, and 5. And we could represent it visually, if I remove all of these lines, as 1, 2, 3, 4, 5, and then a complement is right here, covering all of 3, 4, and 5. So that is the complement. The intersection requires two sets. It requires a set A and a set B. No universe is required in this case. So given A and B, it's all the elements that occur in both A and B. So for instance, let's say that A has 1, 2, and 3 in it, and B has 3, 4, and 5 in it. Then the intersection of A and B is where they overlap. It is this section here containing the 3. So you want to look at common elements. So if I have 1, 2, and 3 for A, and I have B with 3, 4, and 5, really we just check to see which elements are similar, and then that makes the intersection. So the intersection of A and B would be the set containing 3. And that is with an upside down U. The union is essentially whether the element is in A or in B. It can be in both, it can be in just one. So if we have A and B, we'll use the same sets as last time. We'll put 1, 2, and 3 in A, and 3, 4, and 5 in B. And in this case, A or B just says we take all of the elements and we put it in a set. So visually, this would look like both of these sets completely covered. So A intersection B would be the set containing 1, 2, 3, 4, and 5. We could write 3 twice, but remember that repeated elements don't count. But that is a good way if you want to make sure you're including every element, is just write out all of A and then write out all of B. The last operator I want to talk about is the difference. So A minus B. This is sometimes written A backslash B or A intersection B complement, which is exactly what it is. And I think visually, it's the best described visually. So if I have 1, 2, and 3 in A, and 3, 4, and 5 in B, if I want A minus B, I want everything in A, but I don't want anything in B, so I remove all of B. In this case, even though 1, 2, 3 was in A, B contains 3, and we don't want 3 in there. So A minus B would just be the set containing 1 and 2. So I like the minus symbol for this, mainly because it's kind of exactly what it says. You take everything in A, and then you subtract whatever's in B. So A contains 1, 2, 3, B contains 3, 4, and 5. Oh, 3 is in A, but 3 is in B, therefore we're going to subtract that 3 and just be left with 1 and 2. That's how I like to think of it. It's a nice way to ease into it without any formal definitions. So now that we've introduced all the operators, let's do some practice exercises. The first one, we have A is odd numbers less than 10, B is multiples of 4, and C is the squares of the first 4 numbers. Okay, if we want A union B, we just write out everything in A, 1, 3, 5, 7, and 9, and then we write out everything in B, 4, 8, 12, and 16, and that is A union B. It is everything in A or B. C union B, well, with C union B, we want the common elements. So in B and C, they both have 4 and they both have 16. Therefore, C intersection B will contain elements 4 and 16. C minus B is everything in C minus everything in B. So let me demonstrate this specifically with what I mean with subtraction in mind. Let's write out everything in C. 1, 4, 9, and 16. Now let's subtract things that are in B. Well, 4 is in B, so let's get rid of it. And 16 is in B, so let's get rid of it. So now we're left with the set 1, 9, and that is exactly what C minus B is, or C difference B. Okay, finally, the empty set intersection B. Well, the empty set intersection any set is just the empty set. Because there's no elements in the empty set, so there's nothing in common with the empty set in B. There's no common elements. So that is set operations. If you have any questions, please leave them in the comments below and I will do my best to answer them as quickly as I can.